Yes.
Yes, let me see. Two cubes, cube X and cube Y of different sizes show and the different initial temperatures are placed in contact and okay, this normal situation, the mix of the gas cube has high temperature at the time. Two cubes at thermal equilibrium. Okay. Connect energies.
I mean, this one's pretty simple. It has to reach equilibrium, so it has to end with an equal sign, so that already cancels out A and C. So it can only be B or D.
Yeah, okay, but it's very simple because you are thinking about the macroscopical thermodynamical rules.
Yes.
Okay, we know if you have two systems with different temperatures, the systems will have equal temperatures in some time, right? But in microscopical world, the microscopical world, the things is sometimes is different, right? Here you are right, because in this situation we have the relationship between kinetic energy and temperature, but you need to be you need to be careful about this, right? But okay, you are right here.
Mm-hmm. This one.
Right, two, let me see.
This one is really easy, but yeah.
Oh, okay. The first rule of thermodynamics. A sample of ideal gas is a container with a movable piston. Oh, okay, the ideal gas. And during the interval, the piston does. Okay, just putting this equation. So
yeah, it's literally just plugging.
That slide was more harder than these questions.
Yeah.
Okay. Okay. This is very cool for us. Here is right to a sample of all your specific hat. All right. You need,
fine.
this equation is very useful.
Yes.
For another for a lot of things. For example, how can I say potential?
Potential.
Right. Sometimes we will this equation for another things. So I suppose this is the most important equation here, because sometimes we need to use this for gas, for example. So we can change some terms here. You need to be very smart about this, because this equation is hard sometimes. If you, for example, need to use diatomic gases or polyatomic gas, this equation will change a lot. Okay? But here is very easy.
Great.
Okay, entropy. Oh, entropy sometimes is hard.
I didn't guess exactly. I just guessed.
Oh, let me see. Entropy is easy for you? Do you understand the idea about entropy?
No.
Entropy is a very strange idea in physics. But here, we don't need to be philosophical about the entropy. We just need to use the equations, right? So let's focus in this situation. Let me see the question first. Okay, the variation of entropy, right? Okay. In option A, the entropy is constant, but this is a wrong affirmation. Because entropy in an isolated system involves the transfer of between the bodies in different temperatures ever increase the entropy ever increase in this situation. Okay. When you have different temperatures, this is a law, the law of physics. B, entropy decreases a constant value. This is wrong too, because the entropy never decreases in a isolated system. Only increase or constant. Okay, so B wrong. C, the entropy increases until it reaches a constant value. Yeah, entropy will increase the more temperature high to the less temperature, until a thermodynamic equilibrium. Okay, amazing. And the entropy change cannot be known without knowing the initial entropies of each individual blocks. This is more sophisticated answer, but it's wrong too, because for the second law, the entropy will increase regardless the value of the initial entropies. So you are right about the entropy in this situation. The entropy, a lot of time increase. Okay.
Okay. And then this one.
Another one. You are right. You are right in all the questions.
No, I'm not. I swear. I have a lot that I did wrong.
Oh my God, this is very sad. But I suppose it is enough to you. And I mean, you are good in this subject, because
No.
this subject is the most hard subject in physics. It's
Uh,
more confused than others. The others have more sophisticated math, but here the interpretation is very hard. You understand?
No, I'm
Yeah.
not good at it. I promise. This is like a group thing also. Like we did this in groups, so I don't even know which of these I fully understood. But yeah.
But you need to be more confident because you are good. Okay. D is right here. But why? Then the kinetic energy, a single atom, can be more, equal, or less than key in this situation,
Yeah.
because the statistic distribution about the energies, I like that first image you
Question.
showed to me.
Yeah.
Do you remember?
Yes.
Yeah,
I
you have
understand.
this. Okay, so just very easy if you understand that situation, the first question. Okay, let's go to the next one. I have a really good book about this subject,
Oh, awesome.
but yeah, but this book is the graduation book. But I suppose is very cool to you read a graduation book, because have more examples, more specific explanations. And I
Yeah.
suppose you need this to be more confident, because you really know how do some math here. This is very easy to you, but you need more theory, you understand?
Yeah.
Yeah. So I will search this book in English for you, and I suppose is your mother language is English, right?
Sure. Yeah.
Okay. So okay, let me see this question,
Okay.
because I have this book in Portuguese only.
Yeah. I
But the
figured.
author is American, so I suppose. Let me see. A sample of ideal gas is a closed container of a constant volume V. The gas initially the temperature. Oh my God, this is very easy if you use the
Yeah.
law of ideal gases. So
Yeah. It's just saying if. What is it saying? It's just saying. Oh, temperature. Yes. So if T gets doubled, then P has
yeah,
to get
because
doubled.
this law is more interesting if you use this form here. Can you see my
Yeah. Yeah.
screen?
I can see it.
Okay, so I prefer this version of this law, okay, because the pressure, volume, and temperature are state variables. What's this in physics? State variables don't matter the path to change the initial situation to final situation. only the values, right?
Okay.
So this value, this arrange pressure times volume over temperature is ever the same value, right? The value, of course, is the number of moles times this constant, right? So if you compare two situations, you don't need this. You can just use this form, right? So in this situation, we have the constant volume, so we can um, simplification this. So you have just this. If you the gas after the temperature is double, okay, we will double the temperature, but to this thing is equal to this thing, we have double the pressure too, right? Because these numbers will simplify, and you will have the same thing in the both sides of the equal, right?
Yes.
So you can ever use this form. Is more easy to us here.
Okay.
Okay, let's go to the next one. Oh, okay, transfer of energy. Okay, let me see.
This one's also simple. You just put them into the equation, right?
Yeah, very simple.
And then
Okay,
it's values.
let's go to the next one. But again, this microscopical situation. So pay attention in these situations. Okay. Again, just put the values in the equation.
The equation, yeah. This is
If you
fine.
know the equation, is easy.
It's always the same equation.
Yeah, yeah. But this equation have a lot of changes if you use this in a gas situation, because this is not a gas situation, right? It's a block with a specific heat. But if you
Yeah.
use this equation in a gas, you will have a lot of problems. It's
Yeah.
very hard because this equation will depend about the quantities of the particles in your molecules. So it's very hard. Okay.
This one I got wrong. Another one.
Wrong. Oh my God. Let me see. Let me see. Just
Oh.
a second.
Let's see it here.
I need this situation bottle and a cylinder. Okay. Okay. You have a lot of options here. Increase, I mean the same. Right. We need to know about the entropy in these systems. For example, the first option, the entropy of the system increase, and the entropy of the neighbors is the same. This option is the right option, because when you have a gas expansion, the entropy, the system increase, because you have more possibilities for your particles, right? You can understand the entropy. You can understand the entropy with possibilities. If your system have more possibilities to stabilize, you have more entropy, right? So in this first situation, it's right, because the gas expansion increased the entropy, but the thermodynamical isolate don't allow about the change of the entropy in the neighbors, right? So change in the system, but in the neighbors is the same. For example, B, the entropy of the system decrease. Wrong, never decrease. All right. The entropy of the system is the same, and the entropy of the neighbors is the surroundings. And surroundings is a better word. Surrounds increase too. Is wrong, because in the surroundings don't change in this situation. because the system is isolated of
Mm.
the surroundings, right?
Okay.
So is a why you wrong this?
I
Why you
don't.
put because you don't understand the idea of the entropy. You need to see in this situation you have the surroundings isolate about the system, right? Because you have a bottle and a cylinder, so the surroundings don't change anything here, right?
Right. Okay.
So the entropy is the same.
Okay.
Okay.
For the
For
system.
example, if you increase entropy in your home,
But then
in
how
my
can
home,
it change for the surroundings?
yeah, don't change in the surroundings.
There
Remain
is
the
a
same.
change in the surroundings.
When?
Oh, no.
Eight is the right answer, right?
Yeah.
Yeah. So okay. Oh my god, yeah. We are right now.
Mm.
Yeah. For example, this is easy if you do a real example. For example, if you increase the entropy in your home, in my home, doesn't change. Why? Because here is not here is isolated about your home because it's very far. Okay,
Yes.
so in this situation, the same thing.
Okay. I understand.
Another right
This was
answer. Let me
fun.
see. Just use the gas ideal equation. Very easy. You need to be careful about what is moles, what is the volume, what is the quantity of molecules. So
Yes.
if you pay attention to this, we are not wrong. Oh my God, again, the heat equation. But in this situation, we don't have values. But in this situation, the question asked to us about a ratio, okay? A ratio of the change, a ratio.
Oh, I
So,
wish.
uh, yeah, ratio. So you just write two equations and divided the equations. So it's enough to take the ratio because you don't need the value of it, delta T1 and delta T2. You don't need only the ratio. So you write the equations and do the division about there, right?
Mm-hmm.
Okay, let's go to the next one.
Yes.
Here you are wrong. Let me see. Mhm, mhm, mhm. Mhm. Here's more hard. Here's more hard. I will explain to you. Let me see. The pressure increased and the pressure stayed the same. Okay. We need to understand the law of the ideal gases, right? PV equals N, Boltzmann constant times temperature, right? So the volume in this situation is the same, is constant. So the volume of the molecules of the gas too, because the system is closed. And the temperature increased because gas is because you are putting heat in this energy in this system. So the option A, the pressure increase. This is right because when the temperature increase, the kinetic energy, the mean kinetic energy of the atoms increase too. So the atoms um, the atoms hit the walls the system with more force, more intense, right? Particles hit the walls with more force. So this increase the pressure. Okay?
Mhm.
Do you understand? So the situation is only a microscopical vision about this microscopical situation, right? Pressure is this. Pressure is the force which the particles hit the walls of your system. So if you increase the temperature, you increase the speed of the particles, you increase the force with these particles hit the walls, right?
Okay. Sorry, I need a minute to process.
So the right answer is A.
Hmm.
Yeah. You put B, the temperature increase, because an increase in temperature always corresponds to an increase of pressure. No, this is not right, because in some gases we have a constant pressure, right? You change the temperature or you change
Oh, the volume.
but the pressure is the same.
Right.
Yeah.
Okay. I
If you
understand.
control the pressure, is for example, in a plane, in airplane, you have a constant pressure,
Yes. Okay. I
but you
understand.
change the temperature, we change the volume of the airplane. This is very strange, but
That is true. You can.
yeah.
Okay. Awesome. This one.
Okay, this is very long, like a Bible,
Yeah,
but I suppose it is easy because
because
it's
I
a
got it right.
container. So let me see, it's a gas. Ah, gas. Oh my god, so it's not easy. Uh, gas is ever hard, but you
Yeah.
put the right answer. The temperature of the gas container Y will decrease because energy is transferred from the gas. Yeah, this this is very easy. Okay, so we can go to the next one because you will um,
Got it right.
increase the volume. So in that situation, the energy will decrease. So we have a graph pressure.
Oh, this is also easy. Don't worry about this one.
Yeah. Okay. In this situation,
Just
is big.
the change.
Yeah.
Yeah, it's fine.
Uh, in this situation, but if you have this graph to solve some energy problem, you will have problems. This is will be hard because when you have this microscopical situation, pressure, volume, temperature, is easy. You have all the informations to put in the equation, for example. But sometimes you have this image to using an energy problem with heat and work and thermodynamical energy. So is hard. But he in this situation is easy. But okay, we can go to the next one. First law of thermo. Okay, again,
Same thing, but they give you numbers.
just the area. This situation is easy. When the question asked to us the work is easy because you need only do the area of the graph, right?
Mhm. Yes.
Yeah. Okay, this is a lot of theory. Just a second. Okay. The answer, they will come to semi-equilibrium temperature because the entropy of the system is the highest when the system is in thermodynamical equilibrium. This is a law. This is a law of physics. So if you know the laws, you know the answer, right?
Hmm.
Okay, so the another answers is not the laws. Okay, you are right. Just like that.
Okay, and we're done. That's the last
You
question.
are done. Just okay.
I got a few wrong. I got
Okay. So
No.
you are good in this in subject yet, but I suppose this
I mean,
will,
I'm fine when it comes to group stuff. I mean, I'm not very good at testing in general.
yeah.
So that's
So
where my grades go down, is in tests.
I understand.
This one
So,
I did terrible. So
oh my God.
4 out of 7.
So,
So
uh,
do we have time actually? No, we don't have time.
I suppose we have. Can you show this to me?
Yeah. Do we have time?
Okay. Yeah.
Okay.
Okay. Let's go. These two answers. Oh.
Yeah, so I got one right, one wrong.
So let me see. I will explain to you this in just a second. When we have collisions between atoms, collisions ever do this transfer of energy. So this is very easy. You put this right, A is right, but you put B too. Atoms with high kinetic energy move along the road from the hotter end to the cooler one. No, no. Because in this situation, in this microscopical situation, what's move is the atomic vibrations. So the individual atoms don't have this macroscopical vision, right? The individual atoms know only the mass of atoms, the probability of atoms, right? This is a little quantic situation. You
Okay.
understand? So you cannot say about the atoms think they like things in the real world, in the macroscopical world. Okay, so this is wrong. This is very very sad. Say, to me, it's very sad to say this to you, but B is wrong because the quantical world is different to the microscopical situation. Okay, in the microscopic situation, we have this conduction, right? Is very common. We touch something in the fire, and the time it pass, and your hand burn because the heat will transfer to you. But the atomic world is not in this way, right?
Yeah.
Because this is the law, the nature law. So you can think, you can ask God or something. The average energy is transferred from atoms with greater speed to atoms. Here is the true. Like that first image you showed to me. We have a distribution of probabilities, right? So the energy, the energy will be to the atoms with smaller speed, but not an individual atom. You understand? A group the atoms. For example, I need to show something. Will be very instructive to you. I will show in my screen.
Yes.
For example, we have this Maxwell-Boltzmann curve, right? It's a probability curve, P
Yes.
and speed. But if the time pass, what will change in this curve? This curve will be more flat.
Yes. It just goes constant.
Yeah. So this is because this transfer of energy. The question C. Do you understand?
Okay.
And in a system, in a not isolated system, the particles go out to the system, like the clothes in the sun, right? The more energy particles, the more energetic particles will go out to the clothes. The clothes will lost. You will lose the water because I don't remember the word in English. Just a second.
No problem.
The word is the clothes will dry. I don't
Yes.
remember the word dry, but why the clothes will dry? Because the more energetic water particles will go out to the clothes. Okay,
Mm,
these particles here, they will go out. So the curve will be flat because the most energetic will go out to the clothes, right?
mhm.
Okay. So B is wrong, C is right. Photons emitted by atoms with greater speed are absorbed by atoms with smaller speed. What? But this is not anything in this situation. Let's go to the next one. Okay, the gas filled balloon. This is real right. Okay, this is only work with the first law of the thermodynamics.
Wait, sorry. Just really quick. Until when is this class? Because it's already 9. So.
Our class finish in 3 minutes.
Oh, okay. What?
But if you need finish it now, you can finish.
No. I was just wondering because I didn't want to. No, we're fine.
Okay, let's go to the next one.
This is the next one.
Okay.
Oh, I mean, I got it right. Do you want to move on?
Yeah,
Okay.
because I say to you in this question is only putting the first law of thermodynamics. So it is. Let me see now. Now you are wrong.
I got this one right. I got this one wrong.
Yeah, Km and Lm. Yeah. In this situation, for which of the following pairs of paths along this process is equal amount the network, you need to take care about not only the area but the sign of the value of the energy, right?
Mm-hmm.
If you choose the wrong path, your sign will be negative. So this was your error here, I suppose. Okay, because when you have a clock, the clock, how can I say this? Uh, if you take the wrong path, the energy will be negative because the work will be by the system, not on the system. This is a very theoretical situation, very boring situation too. You need more time to understand the situation, but what you need pay attention here is only the sign. This is only the unique thing you are wrong in your answer, right?
Mm.
So unfortunately, now we don't have time to do this, but the work in your path have two different signs because this you are wrong. Okay.
Mm-hmm.
Okay, so I suppose is this. I am very happy with this class because you are very good, but really, I suppose you need more theory.
Yeah.
So I will search that book for you and I will send. Right?
Thank you. That would be really nice.
Uh, thanks.